I know the syllabus is split up into 3 sections. The unit is split up into 3, but I'm splitting up into 4 because you want to, these are breaks, okay? So these are not continuous. I mean, like the thing that they've mentioned in the syllabus, it has basically approximation of integrals, and they put on calculation of Legendre polynomials also there, but it's not related to that at all. So what we will be doing today is we will be starting section 2 of the 4 sections that I mentioned in the first class. We will be doing approximation of integrals. Okay, so yeah, so let's get to this. Okay, so yeah, okay, so quadrature as box counting. So what does quadrature basically mean? Quadrature basically means that you're trying to convert something into boxes, into quadrilaterals or square boxes. Okay, so what is integration all about? Basically, it's trying to discretize things and count them. Okay, so discretize things as it goes to a very small infinitesimal portion, and then you start counting them. Okay, so the whole idea of having some computational technique integrated into this is to do box counting essentially, even though that is not, I mean, like that is not what you exactly do, but because of this primitive technique called box counting that we've done before, and I don't know if you kind of like noticed this. So when I was in 12th grade, we had this experiment where you would have, let's say, a leaf. Okay, so this is okay, my leaf is horrible. Yeah, okay, so you would have, say, a leaf. Okay, and we had to compute the surface area of this leaf and then determine the amount of oxygen that it's going to give out, or irrespective of your sunlight or whatever that's coming into this. So you would have to determine the amount of O2 levels that are given out and stuff like that. So what we would have is basically what we would do to calculate the surface area of this leaf, okay, would be to take a graph sheet. Okay, so we would have a graph sheet and we would place this or stick this, not stick exactly, but we would place this leaf onto this graph sheet. Okay, so we would place this leaf onto this graph sheet and then we would outline it. Okay, so once we get the outline of that, we would get the outline of that. Okay, we would get the outline of the leaf and then we could compute the area. And how do we compute the area? We would start counting boxes. So if there is, say, 10 whole boxes that are covered, okay, so because of the way the leaf is, okay, there are sometimes you might only cover certain parts of it. Like, let's say, if this is the leaf, okay, you might only cover 2 whole squares and you might cover, like, say, half of 1 square. So then we would start counting it as 10 into 1. Okay, so if there are 10 squares, 10 whole squares that are covered, if there are more than half covered, okay, so more than half of a square is covered, then we would say, okay, fine, 3 by 4. Okay, if more than half of a square is covered. If approximately you get half of a square covered, we would say into 1 by 2. And then if we have, less than that, we wouldn't count them at all. Or if we would count it as 1 by 4 and then we wouldn't count it at all. So by doing this, okay, so let's say you have 10 squares, 10 whole squares, 3 by 4 covered, let's say 8 squares, half covered 2 squares, and then 1 by 4 or quarter covered 1 square. Okay, so if that is the situation that we have, now we are able to compute the area of the leaf, okay, the surface area of the leaf. So we would use these techniques to compute the surface area of the leaf and then determine that, okay, oh, so this much O2 at this particular temperature at this particular time of the day might be generated, or this much CO2 might be absorbed by this particular leaf or whatever. I'm not that great in biology. I just know a little bit of it. Okay, so yeah, so the traditional way to do numerical integration by hand is to take a piece of craft paper and count the boxes or quadrilaterals lying below a curve of the integrand. Okay, so basically here you have usually you have a curve, okay, and then you count it. But here, when we are talking about a leaf, you did not have a curve, you just had very, very rugged kind of outlines. Okay, So for this reason, basically, when you talk of numerical integration, okay, since the essence of this is to count boxes, okay, we call this as numerical quadrature. Okay, so what you're doing is you're taking, let's say you have this function right here. So this is f of x and this is x. And you take this function, you're basically converting this whole area into tiny little boxes or rectangles, and that's how you're integrating it, right? So this is the essence of it. What we do is when we do integration, we're basically saying this little interval, say h tends to 0, right? So now what do we do? Let's just okay, so let's just go forward with this. Okay, so basically what we're saying is we have, when we're talking of numerical integration, we can also say it as numerical quadrature, because basically what you're doing, even though the technique is now more sophisticated, basically what you're doing, in essence, you're doing box counting, and that's all integration is. Okay, you're just counting tiny boxes. Okay. So now let's look at the Riemann definition of an integral. Okay, so it is in essence, it's the same thing. Okay, so if we look at the Riemann definition of the integral is the limit of the sum over the boxes, okay, as the width h of the box approaches 0. So what did we say? We're integrating tiny infinitesimal boxes. So what are you doing? You're taking the width of the box and you're multiplying it by the function at that particular, say, point, okay, discretized point. And then you end up getting your integral. So this is what your integral basically is. So what are we doing? So we have this very little or very big, according to how I've drawn it, but very little infinitesimal, imagine it is infinitesimal. So very little infinitesimal box that you have, you take that width that you have here, you multiply it with f of xi. Okay, so why am I saying that? Okay, I'm saying, okay, fine, there's going to be this entire thing that I have is going to be discretized into one whole stuff. So I'm going to have this represented by an I. Okay, so the first h is 1, the second h is 2, the third h is 3. Okay, it's not continuous, it's been discretized, and that's the Riemann definition of the integral. So h is your width and this guy is your function at that discretized point. Okay, so that's why you have f of xi at that particular point. Okay, so now since we've got the basics of this, let us clear all of this. Let's go to this. Okay, so the numerical integral of a function f of x is approximated as the equivalent of a sum of over boxes of height f of x. So you have a box of height f of x and a width w, and you take a product of those two and you sum it up. Okay, so this is similar to the Riemann definition of the integral. Okay, so now here, what is the fact that is distinguished from what is distinguishing it from your Riemann definition? There is no limit here. Okay, there is no limit here, and does not say, okay, let's go to very tiny limits. In your Riemann definition, you have a limit. In this definition that we're going to be using, this is typically used in all algorithms, most algorithms to solve your integral. This is basically your standard form of your integration algorithms. So here what we would do is we don't have a limit. Okay, there you do have a limit. Now here the function f of x is evaluated to say about n points in the interval that you have from a to b. Okay, and the function values f of I, f of xi are summed with each term in the sum weighted by wi. Okay, so you've got a weight associated with that particular point that you have. Okay, you do it for n number of points. Okay, so now I will start a poll. Okay, this you have to be a little careful. Okay, let's read the question once carefully. For an indefinite integral, the answer after evaluation in general will be a number, a function, a number or set of numbers, a function or set of functions. Okay, so let's just read it again. For an indefinite integral, what do you mean by indefinite integral? You do not have your points given to you, right? You're going to be saying, okay, fine, this is going to be some term plus a constant. Okay, so some term plus a constant, that's how you see it. So the answer after the evaluation in general, will it be a number? Will it be a function? Please note, I have mentioned in general. Okay, so please note, in general, what do you call it? Okay, not specific, but in general. a number, a function, a number or a set of numbers, and a function or a set of functions. So let me just start that poll now. Okay, so you've got about a minute's time left. Okay. And please ping in your answers. I hope you haven't slept. Thirty seconds left. Okay, I'll give you 10 more seconds. And then I will stop the poll. Okay, I'm ending the polling now. Okay, so 47 of you guys voted out of a participant of, let's say, 51. Okay, fine. Okay, so majority of you guys said a function or a set of functions. Okay, let me just share the results with you so you can see them. You have a number, a function, a number or a set of numbers, a function or a set of functions. Okay, and okay, so let me just stop sharing the results. Okay, so let me just show you, okay, what we get. So let's do integral, okay, x squared dx. Let's do this. Very simple integral. What do you have? You say x to the power of 3, okay, when you integrate it, divided by 3 plus c. Okay, so what do you get when you integrate an indefinite integral? Okay, you get a function. Okay, some of you ended up saying the differential equation answer. Okay, you don't get a function or a set of functions. No, you get a function. Okay, just a function. Okay, what if it was a definite integral? If I put -1 to 1 x squared dx, what do I get? I get x to the power of 3 divided by 3 -1 to 1. I get what? 1 divided by 3 minus 1 by 3. So that's going to give me a 2 by 3, right? So I get a 2 by 3. So that becomes a number. Okay. You do not have a constant of integration. It's not, so you can basically write integral of f squared dx is equal to a function of x. You get a function. That's all you get. You do not get a set of functions. Okay. So let's look at this. Okay. The limitation of the Gauss-Legendre integration rule is the interval. It is, wait. Okay, so one of the limitations, let me just get this, okay, clearly. One of the limitations of your Gauss-Legendre integration rule is that it is restricted to -1 to 1 region, okay? So if you want to do an integral, say from 3 to 5, okay, you need to change it to the realm of -1 to 1. And there are certain techniques to change that, and we will discuss that. Changing that integral, we will discuss it in the next session. Okay, so the required integral that you need is -1 to 1 f of x dx. So let's make sure that we remember this concept. Okay, the limitation of the Gauss-Legendre rule is that the interval is always restricted between -1 to 1. Okay, remember that, because there's going to be a question and you're going to have to answer that. Okay, and if you do not answer that, I'm going to be pretty upset about this whole thing. Okay, not that it would matter to you. Okay, so the required integral is integral from -1 to 1 f of x dx, and this can be written in this form. Okay, so what are you doing? We're going to be writing in terms of certain parameters. So you write integral from -1 to 1 f of x dx is equal to lambda 0 f of x naught plus lambda 1 f of x1 plus lambda 2 f of x2 and so on till lambda n f of xn. Okay, now the approach of undetermined coefficients here is followed. To determine the unknown coefficients is what our task is. Okay, so we need to find out what these lambda i's and lambda xi's are. Okay, Now, the quadrature rule, like I told you, is an approximation of the definite integral of a function. What are we basically doing here? It's this peculiar thing. It's basically like a subset of something called the Gaussian quadrature. Okay, and the Gaussian quadrature, what it does is so when we're talking about your Gauss-Legendre method, it's like a subset of this Gaussian quadrature. So what it does is it tries to get the best estimate that you can by picking up ideal values of xi. Okay, so what are we doing here? We're going to pick up points. Okay, we're going to pick up points. Let me get this clear, because we're going to come across different kinds of points, different types of points in the Gauss-Legendre method. Okay, so what we're going to do is, let's say we're going to do Gauss-Legendre method in the first point using 1 point, Gauss-Legendre method using 2 points, Gauss-Legendre method using 3 points, and so on. Okay, we would do it up to 3. So at which you can evaluate f of x. Okay, so there are certain conditions to that. Now, like I said, the Gauss-Legendre method is a form of your Gaussian quadrature for approximating the definite integral of a function. Again, remember, definite integrals. Okay, we are integrating it from what region? From -1 to 1. Okay, so for integrating over the interval from -1 to 1, the rule takes this form: integral from -1 to 1 f of x dx, and you have sum of I is equal to 1 to n wi f of xi. You have certain weights, and you have certain sample points, and you have the function at that particular sample point. So if n is the number of sample points that I use, wi are the quadrature weights, and xi are the roots of the nth Legendre polynomial. Okay. So let's look at this. For any integration, we need to transform the range from AB to your -1 to 1 region. Okay, so that transformation part, we will do a problem on it, and we will kind of like look on it elaborately in the next session. What our task is to do is to look at how can you do the Gauss-Legendre method in 1-point form. How can you do the Gauss-Legendre method in 2-point form? How can you do the Gauss-Legendre method in 3-point form? Okay, and there are problems that are going to be associated with this. So whatever is boxed, the equations that are boxed, you take a piece of paper and you write it down. Okay, because that is really important. And I will not send the slides immediately. I will only send the slides after you've done your test. Okay, so after you've done the second Google form test that I'm going to send in for today. Probably I'll send it after 4 p.m. So because I don't want to burden you with too much work, I'll send it after 4 p.m. and I will keep it open till about 6 p.m. so you can submit your answers in there. Okay, so once this transformation is done, what we can do it is we can express it in terms of a series expansion or a linear combination of the functional values at different nodal points. So integral from -1 to 1 f of x dx is equal to summation of k is equal to 1 to n lambda k f of k f of xk. Okay, f of xk. Okay, now what do? You substitute that particular point. What is this basically? So this is basically your xi. Okay, so this one that you had was in general your xi that you had. So you have an x1, you have an x2, you have an x3, and so on. Okay, so you just expand that out. Now let's look at this. Okay, so how do we approach this? Like I said before, first we will find out the undetermined coefficients. Now, again, I'm reiterating this. The integral has to be changed if it is not in the -1, 1 realm. Okay, it's not in the realm of that. You have to change it into the -1 to 1 realm. That's how you go about doing this integral. And then you will find out the undetermined coefficients, and then you will go forth. Okay, so okay, so let's look at this. The Gauss-Legendre integration methods, there are of 3 types. You have a 1-point formula, 2-point formula, and 3-point formula. Why are they called so? Because you use 1 point to evaluate the integral. If you have 2-point formula, you use 2 points to evaluate the integral. If you have 3-point formula, you use 3 points to evaluate the integral. Okay. And we shall look into the error analysis for each of them, although it is not necessary. So let's do this question. In what interval can the Gauss-Legendre integration rule be applied? Okay, so is it from the A, B region? Is it 2 to -2, 1 -1, -1 to 1? Okay, so I will start the particular poll now. Polling number 11. Okay, so put in your answers. Fifty seconds left. My God, you people. The answers are just impeccable. Twenty seconds left. I will give you 10 more seconds if you want to put in any last minute answers. Okay, so I see 44 out of 52 have voted. So I'm going to end the poll now. Okay, I will share the results with you people. How many times did I repeat this, that the interval is from -1 to 1? Okay, fine. You guys answered option C. It's fine. I get it. You did not see the minus sign properly if that is the case. But how about A to B? I told you that the GL method or the Gauss-Legendre method can only be applied to your definite integral, and it has to be in the range of -1 to 1. Otherwise, you cannot apply it. I just told you that there is a technique for converting it from -1 to 1, from let's say from a random A to B to -1 to 1. And I told you that I'm going to be teaching you that. I repeated this like 3 or 4 times. This basically tells that you're not paying attention when you're listening to this whole thing. And I repeated that 3 or 4 times so that I can get like more number of people getting answered. For the 54% of you who answered -1 to 1, good, well and good. But the others, like, please, like, don't just click in random things because you're just excited about doing plugging in multiple choice questions. Okay, don't just do that. Read the question before you actually do it. Okay, so I'll stop sharing the results and then let's go on to this. Okay, so we will be starting off with the 1-point rule. How do you write the 1-point rule? Basically, you say integral from -1 to 1 f of x dx is equal to lambda naught f of x naught. Okay, now what do you need to find? What is our next step? Our next step is to find out the undetermined parameters. Okay, what is that? Your lambda 0 and your lambda x. So there are certain conditions to this 1-point rule. You cannot have your lambda 0 to be equal to 0. Okay, you cannot have your lambda 0 to be equal to 0. Now there are two unknowns that you need to find out, which is lambda naught and x naught. Okay, so we will look at the polynomial. Okay, so see, when you have to find them, you need to look at the approximation of this function with the exact polynomial of order p. So what we're going to be doing is we're going to be saying, okay, fine, let's look at a polynomial of order 0, okay, which is what, 1 or whatever, or constant. Then we will look at a polynomial of order 1. Okay, so if the polynomial is in variable x, you say x. Then we will look at a polynomial of order 2. Okay, but here, what are we looking at? We just have a lambda naught and f of x naught. So we will be stopping it with the order 1. Okay, now how does the error creep in? The error creeps in when you have some kind of a function which cannot be used. Okay, so basically, let's say that this 1-point rule has been formulated by using f of x equal to 1 and x. Okay, so now if you put in an value of x squared, you're not going to be getting the exact value of that integral. Okay, so if you're trying to compute this using the 1-point rule, surprisingly you will find that it is 0. But when we did this problem earlier, I hope you remember, we just did it, we got about a 2 by 3, right? But when you're doing it using the 1-point rule, because it is out of the bounds of that particular polynomial that you've used to calculate this 1-point rule, okay, because it's out of that, it's not going to be giving you the exact answer. So it's going to be giving you 0. Okay, so let's just look at this. Okay, so if the polynomial is of order greater than p, it will give a non-exact term, and then we will have an error existing at that point. Okay, so you cannot use it for polynomials of order greater than 1 in the 1-point rule here. Okay, so now how can you write the error constant? The error constant will be the actual integral itself that you do, subtracted from what you found using your Gauss-Legendre method. Okay, so that's how this is. And this is the error term that's given. So here, the C that you have here is a constant, the error constant that you have. And then you have a p plus 1 factorial, which is basically the order of the method. And then you have the p plus 1th derivative of this. So xi is basically a term that's there between your a and b. Okay, so what is a and b? A and b is the bounds of the actual value, the actual integral that you need to evaluate, not just from -1 to 1. A and b is not -1 to 1, but the actual value of the integral that you need to evaluate. Okay, so now how do you make the formula exact for f of x is equal to 1 and x? Okay, so it's not very prominent. Let me just box that. Okay, so f of x is equal to 1. You need to make the formula exact for f of x is equal to 1 as well as x. So you have an f of x here equal to 1. Okay, so you will say that it is equal to 1. So what do we get? Here integral from -1 to 1 f of x dx. Here this guy is going to be substituted as 1. So when you integrate that, what do you get? You get an x, right? And you evaluate it from -1 to 1. So you get a 1 minus of -1, which is going to be equal to 2. Okay. What is f of x? You had from your Gauss-Legendre method, you had a lambda naught x naught. So here, what do you get? Here, you know that your f of x from here will be 1. Okay, so you know that 2 is equal to lambda naught into 1. That's how you get this part. Okay, now let's do the second part. Okay, now first, what do? You say f of x is equal to x. Okay, you need to evaluate this from -1 to 1, f of x dx. Okay, so what is f of x? It's x. So integral from -1 to 1, x dx. Then you get an x squared divided by 2 once you integrate that from -1 to 1. And what is the value of that? That is going to give you 0 because you have your -1 squared, right? So you have 1 divided by 2 squared minus of -1 squared divided by 2. This is going to give you a plus. So this entire thing cancels out and becomes 0. Okay, so 0 is equal to lambda naught x naught. Okay, so that's what you get in the second equation. Now you need to find out what your parameters are. So these two are your equations that you have. You have lambda naught is equal to 2 and you have 0 is equal to lambda naught x naught. Since lambda naught is not equal to 0, okay, this is a condition that is there. And also you got that from the first term that you had. We obtain x naught is equal to 0. So now what did you do? You got your two parameters, lambda naught equal to 2 and x naught equal to 0. Now what is the integral that we said? The integral is going to be of this -1 to 1 f of x dx, which you calculated using the 1-point method, was going to be equal to what? It's going to be equal to lambda naught f of x naught. So it's going to be equal to lambda naught, which you have 2, and f of x naught, which is f of 0. Okay. So let's look at the next slide. Okay. So what did we get? We got 2 and f of 0. So therefore, the formula that you have from the 1-point Gauss-Legendre integration formula, it takes this form 2 f of 0. I hope you're not getting really confused about this. Okay, so what did we do? Let's just go back. Let's just review this. Okay, so we're saying that the 1-point rule is given by -1 f of x dx, which is equal to lambda naught f of x naught. What our idea is to do is to calculate lambda naught x naught. How do we calculate lambda naught and x naught? We try to make this 1-point rule, okay? We make it exact. We try to make it exact for f of x equal to 1 and x, so that we can calculate these two parameters, okay? So once you do that, get a 2f of x naught. Now let's say that I want to compute the integral -1 to 1, okay, x dx. This is what is given to me. Okay, I can compute it either using the normal method that you know of, or I can compute it using the 1-point rule. Okay, now I'll compute it using both. Okay, I just did this before, but I'll do it again. So if you're doing it -1 to 1 x dx, you get an x squared divided by 2. From -1 to 1, you get 1 divided by 2 minus, you have -1 whole squared. Okay, this is whole square divided by 2, and you get a 0. Fine. What about the 1-point rule? What is my f of x here? My f of x here is equal to x. Okay, so f of 0 is going to be equal to 0. So 2 into 0, I will get 0. So you do see that it is fine for this. But let's say instead of x, I have an x squared. In that kind of a case, what I will get here is, okay, I will erase all of this. Okay, I will erase all of this. Okay. In that kind of a case, what will I get here? I'll get integral from -1 to 1 x squared dx. So I'll get x power 3 divided by 3. From -1 to 1, I get 1 divided by 3 minus of -1 divided by 3. I hope you know that the power is 3. So -1 power 3 is going to be -1. Okay, I'm not going to be going into very minute algebraic things. So you get a 2 by 3. Okay, so this is the exact value that you have. But in the 1-point rule, if I try to compute this, your f of x is going to be x squared, right? From here, your f of 0 is going to be 0. Okay, so 2 into f of 0 is what? It's going to be 0. So this doesn't work for polynomials other than the order of x power 1. Okay, so it does not work. So what do? We have a 2-point rule, and then we have a 3-point rule. Okay, so that we can expand this whole thing. Now let's just look at the error constant. Okay, so c is equal to integral from -1 to 1 x squared dx minus 0 is equal to 2 by 3, which I kind of like just showed you. So what did we get from your Gauss Legendre method? We got a 0. This is the exact value. Okay, so the error constant is basically going to be 2 divided by 3. Now let's look at this. So the error term, what is given here, Rn f of x is equal to c divided by 2 factorial. Let's just take it as such for now, okay? Because I don't want to go ahead and derive the error term. It's going to take it's basically equivalent to, you know, what we had done before, but I don't want to do that because these are not going to be coming in your calculations. Okay, these kind of questions are very rare that it's asked. What's going to come is they're going to ask you to compute the integral, either from -1 to 1 region, or they'll put it as 0 to 1 region. They'll ask very simple problems. Okay, they're not going to be asking very complex problems. They're going to be asking simple problems, unless of course the person who sets the paper is a real annoying person. They're going to be asking very, very simple problems. Okay, so you have an R of n f c divided by 2 factorial. So you take this error constant and you substitute it into this error term, and you have the second derivative xi. Okay, so xi here is from -1 to 1. Okay, now let's look at 2-point rule. Okay, so the strategy is the same. I will do the 2-point rule, and then your homework will be to do the stuff for the 3-point rule. Okay, so the 2-point rule here is given by integral from -1 to 1 f of x dx is equal to lambda naught f of x naught plus lambda 1 f of x1, where lambda naught and lambda 1 are not equal to 0 and x naught is not equal to x1. Okay, so I hope you get the idea that if your x naught is equal to x1 kind of like says that you do not have 2 points, but you're evaluating it with 1 point. Okay, so if you say that your x naught is equal to x1, let me just say it again. Okay, earlier what we found was we had a lambda naught f of x naught. So we're evaluating the integral with 1 point. Here, what are we doing? We're saying that x naught is equal to x1, and we're using the 2-point rule. So we're evaluating it with 2 points. I hope you get that. I hope that point is quite clear. Because it's quite evident that x naught is not equal to x1. Now, if x naught is equal to x1, then you don't have 2 points, you just have 1 point. We're back to square one, we go back to the 1-point rule. Okay, so let's just, and also, let me just make that clear if you have any doubts, whether if your lambda 1 and lambda 0 and lambda 1 are already there. Okay, so even if they are equal, how does it reduce back to the 1-point rule? Okay, so if you have, say, lambda naught x naught, okay, plus lambda 1 f of x naught, okay, what's going to happen? You have a lambda naught plus lambda 1 f of x naught, and I could say that this guy is a new kind of a lambda naught prime f of x naught. So we're back to our 1-point rule. I hope you get that idea. Okay, so there are 4 unknowns that you need to find here. So you need to find lambda naught f of x naught, lambda 1 f of x1. So if you have 4 unknowns, you need at least 4 equations that you need. Okay, I hope you remember the simultaneous equations thing. So if you have 4 unknowns, you need 4 equations. Without 4 equations, if you just have 3 equations, you just can't solve them. Okay, so you need at least 4 equations. So how do we get the 4 equations? So you make the formula exact for f of x equal to 1, x, x squared, and x cubed. Okay, so we push up ourselves to up to x cubed. Now, when is this formula not going to be exact? When you have something like x power 4 going to be attached to this. Okay, so if you have something like, let's say, x power 4, and you try to evaluate the integral, then you're not going to be getting the exact value. There's going to be a certain amount of error. Okay, so you have an f of x, which is 1. Okay, let's start off with the simplest one, integral from -1 to 1. Why have you put 1 here? Basically, you're putting your f of x as 1 because you have f of x dx. Okay, so what are we doing here? Integral from -1 to 1, f of x dx is equal to summation, let's say some kind of an n, lambda n, xn. Okay, so you have lambda 0, lambda 1. Sorry, this is supposed to be f of xn. So you have lambda n, f of xn. So since this is a constant function, f of x naught as well as f of x1 is going to be equal to 1 and 1/3. Okay, now you do the same thing for the next one that you see. So if you have an f of x equal to x, you substitute that integral, and then you get a lambda naught x naught plus a lambda 1 x1, and you equate it up. Okay, why is this 0? Because the actual integral is 0. Okay, so you have lambda naught x naught plus lambda 1 x1. I hope you get the point. We're trying to make formulae here so that we can evaluate integrals. We're not actually doing, it seems illogical. Okay, so why am I doing this for such a simple thing? Okay, we're not doing this for such a simple thing. We're trying to make an algorithm to do the integration for other functions. Okay, not just this. Okay, we're not going to be, when you actually do it in a computer, we're not going to be saying, oh, I want to compute the integral of x squared. Okay, we're going to be computing integral of some really big algebraic function. Okay, and we're going to be trying to approximate the value of it using Gauss-Legendre method instead of trying to discretize and put the limit and stuff like that. Okay, I hope you get that point. Okay, so when you do it for x squared, when we did this integral several times, you get a 2/3, and you have a lambda naught x naught squared plus lambda 1 x1 squared. And similarly, you have a lambda naught x3, lambda naught x naught 3, x naught power 3 plus lambda 1 x1 power 3. And then you get something like this. You get your equations. And once you get 4 equations, you can start evaluating the parameters. But keep in mind the conditions. We have lambda naught comma lambda 1 not equal to 0. Okay, also you have x naught not equal to x1. Okay, so you need to keep these things. Okay, so now this is not 0, x naught not equal to x1. Okay, you need to keep these two things in mind when you're trying to evaluate it. Okay, so let's look at this. Okay, this I suggest you do it on your own, but I will try to tell you how the idea is. Okay, so the second equation, I hope you remember this is the second equation. You need to eliminate lambda 0 from it. Okay, so how do you eliminate lambda 0? Lambda 0, you try to manipulate the 4 equations that you have, and you try to find it out. Okay, so this is the way you do it. So you take your lambda 0 x0 and you take it to the other side. You also have, this is the 4th equation that you had. Let me just point that out. This is the second equation that you had. This is the 4th equation that you have. 4. Okay, and what do? You try to substitute this particular thing over here onto here. By doing what? You take lambda 0 and x0 out, and you substitute minus lambda 1 x1 and x naught squared. Okay, and then you pull out the parameters that you have, but you also know that what? Lambda 1 is not equal to 0, so this cannot be equal to 0. X naught is not equal to x1, and you can reduce things, and you can find out that x1 is 0 and x1 is equal to minus x naught. Okay, so the option of this guy being 0 goes away, the option of this guy being 0 goes away, and then you are just left with this. Okay, so you're either left with x1 is equal to 0, or this x1 plus x naught is equal to 0. So you get x1 is equal to minus x naught. I hope I'm not boring you with the algebra of this, but yeah, I thought I should probably do it for one and show it to you, because one of the one for the 3-point rule is your homework. Okay, and that is, trust me, it's not very easy to solve 6 equations. with powers in them. Okay, you need to do a lot of tricks to do that. But okay, so if x1 is equal to 0, then x0 is equal to 0. Why is that? See, it's basic. I think I have discussed this somewhere, but I'm not sure if I discussed this with you. So if I say x1 is equal to 0, what does it mean? x0 is equal to 0 because x1 is equal to minus x0. Okay, so you don't have a negative 0 separately stated anywhere. Now, if that is the case, then what happens? X1 and x0 are equal. Okay, and this is not possible. This is the first condition that you had when you talked about your 2-point rule. You cannot have x0 equal to x1. If that is the case, then you reduce back to your 1-point rule. I hope you remember what I said before. So now what do you have? You have this x1 equal to minus x0. That is the only thing that can be used. You cannot have x1 equal to 0. And then we've got another couple of evaluations as well. You have 2 equal to lambda naught lambda 1. Okay, you need to substitute this back into the equation, and then you need to evaluate and find it out. Okay, so you need to find out the points x1 and x0, and you know that they're going to be the negative of each other. Okay, so you do that algebra of that particular part, but I will tell you what the points are. The evaluation points are basically plus 1 divided by root 3 and minus 1 divided by root 3. Okay, what you need to find is lambda 0, lambda 1, x0, and x1. Okay, so once you substitute this and calculate it, you get your lambda 1 naught and lambda 1 is 1, and you will try to write down the equation. Okay, so now what did you get? Initially you had lambda naught f of x naught plus lambda 1 f of x1. You substitute your x1 here, you substitute your x0 here, you have your lambda 0 and lambda 1, which are 1. Lambda naught equal to lambda 1 equal to 1. Okay, so that's what you have here. So this is the formula that you're going to be using. Okay, write this down, take this down in a sheet of paper because you need this. Okay, this is the formula that you're going to be using to calculate the integral in this unit. Okay, so the questions to this particular unit, I hope you notice that the question that you get in your question paper has an order. Okay, so the order is basically the first unit comes first, the second unit comes second, the third unit comes third, and the fourth unit comes fourth. Okay, so they will ask you to calculate the integral of this using the Gauss-Legendre method, of this particular function using the Gauss-Legendre method. So what do? You take it for the 1-point rule, you take it for the 2-point rule, you take it for the 3-point rule, and you compute it. Okay, so that's the way your questions are going to be framed. I will show you sample questions probably in the next lecture. Okay, so again, the error constant. Now let's just go back and look at this. So integral from -1 to 1 f of x dx is equal to f of -1 divided by root 3 plus f of 1 divided by root 3. Now, if you want to find the constant, you basically take an x power 4. You take a polynomial that is not exact for the 2-point rule. Okay, so if you made it exact up to x power 3, you made it exact. Now what you need to do is you need to take an x power 4. Okay, so if you take an x power 4, what is the function like? So you had an f of -1 divided by root 3 plus f of 1 divided by root 3. Okay, and you substituted that. Now what do you need to do? -1 divided by root 3 whole power 4 plus 1 divided by root 3 whole power 4. And that's what you get here. 1 by 9, 1 by 9. Note, it's a root 3. So even if I square this, I get a 1 by 3. If I square a 1 by 3, I get that. Okay, so keep that in mind. Okay, so error term, I don't think you really need to know this because problems are not going to be coming. I'm quite definitive that problems won't be coming unless, of course, you're really out of luck. Okay, so here, what do you have? The error term, you substitute your error constant. You have a 4 power 4 integral. How do you get that? Basically, it is p plus 1 factorial. I hope I showed you the basic formula before. And here you have the p plus 1 derivative. Okay, and again, xi, the limit from 1 to 1. Okay, so let's go on quickly. Okay, so this is the 3-point rule. For the 3-point rule, I'm not going to be showing you any drastic equations like this. You're going to be having to do it on your own because it's quite exhaustive. And honestly, it's boring to be doing the algebra. If it's boring to be listening to algebra, it's easy. It's quite engaging to be doing the algebra. Okay, so the 3-point rule is given by integral from -1 to 1 f of x dx, lambda naught f of x naught plus lambda 1 f of x1 plus lambda naught f of x2. where lambda naught is not equal to 0, lambda 1 is equal to 0, not equal to 0, and lambda 2 is not equal to 0, and x naught not equal to x1, not equal to x2. Again, the same reason, you don't want your 3-point rule reduced to 2-point rule or 1-point rule, and that's why you have something like this. Okay, so we have about 6 unknowns here. Now we need to implement the polynomial approximation up to a degree of 5 to get 6 equations. I have 6 unknowns, I need 6 equations, so I take the polynomial approximation up to degree 5. So this means that the up to degree 5 provides the exact solution. Beyond degree 5, I do not get the exact solution. Okay, so this is how your equations would look. Okay, so these are the set of equations that you have here, and you solve them. That is your homework. Okay, so your homework is what? Compute all the unknown parameters for the 3-point rule. That is lambda 0, lambda 1, lambda 2, x0, x1, x2. Okay, all 6 of them. Okay, so once you solve these equations, this is what you get. You get x0, you get x1, you get x2, and you get lambda 0, lambda 1, lambda 2. Okay, so this is how it's going to look. Take this down. Take this equation down on a sheet of paper. Okay, so the 3-point Gauss Legendre integration formula takes integral from -1 to 1 f of x dx is equal to 5 divided by 9 f of minus root of 3 divided by 5 plus 8 by 9 f of 0 plus 5 by 9 f of root of 3 divided by 5. Now again, you notice this is 1 point, this is 1 point, this is 1 point. That's how you get your 3-point, and that's why it's called your 3-point rule. Okay, so you will have to mug up these formulae, and then you will have to evaluate the integral using these formulae. Okay, and it can differ. Okay, so it might not be the exact solution that you get when you compute your integral, and it can differ. Okay, so this is the error constant. What do you do for your error constant? You take an x power 6. Okay, for x power 6, we haven't made this formula exact for x power 6. So you take the integral from -1 to 1, x power 6 dx minus, and then here what you basically do is the Gauss Legendre integration rule for the 3-point integration rule. Okay, 3-point integration rule, and then you end up getting an 8 divided by 175. Okay, and then you substitute this here, you get the error term. Again, not that great, not that important, but I'm just writing it down. If you have a descriptive question, this is going to be useful. Okay, so if you have a descriptive question of 10 marks saying that explain Gauss Legendre integration rule, you could use this as well. Okay, so I am going to be asking you some polling questions. Okay, and then let's see if you answer them right, or if you don't answer them right, and then we will conclude. Okay, so let me just discuss this. The 2-point formula gives exact solutions up to dash degree polynomial. The 2-point formula gives exact solutions up to dash degree polynomial. Confused? Okay. Thirty more minutes. I mean, 30 more seconds. 30 minutes. $15 seconds. I will wait for 5 to 10 more seconds, and then I will end the poll. Okay, I'm ending the poll now. Okay, so yes, the majority of you answered 3, and that's the correct answer. But why is this 2 and 1 and 4? Why is this like okay? So let's just go back and discuss that. Okay, since Okay, so majority of you did answer about 3, but I still want to care about the rest of them. So let's just stop sharing this. What did I say? Okay, so in the 2-point rule, let's just go back and look at the 2-point rule. In the 2-point rule, what did you have? You made the solution exact up to how many functions? You have 1, this is 0th order, 2, x power, sorry, this is x power 2, and this is x power 3. So it's up to 3 that it gives you exact results. Okay, I hope you get that. Why do you do that? Because you need to compute 4 variables. You need four equations to compute the 4 unknown variables. Therefore, you take it up to x power 3. Okay, 4 minus 1, 3. Okay, let me just go back and do another poll. Where is the poll? Oh, okay, I went way back. Okay, so let me just go to the poll. Yeah, okay. So did we do this? The 2-point formula gives exact solutions up to 3rd degree. Okay, so 3 degree, 3rd degree. I should have written 3rd, but anyway, you get the point. How many unknowns would we have in the 3-point rule? 1, 8, 5, 6. Okay, so I'm going to be starting the poll now. Poll number 14. How many unknowns would we have in the 3-point rule? Okay. Okay. 45 seconds left. Thirty seconds left. Ten seconds left. I'm going to be ending the polling now. Okay. Okay, majority of you guys answered 6. Some of you answered 1. I don't even know how that is relevant. Okay, even if you look at 3-point, you have, let's say, 3-point, maybe you try. Okay, so there's no option 3 anyway. But how would we be able to compute? I mean, like the 3-point rule with just one unknown. The basic idea is that you have 3 points in your formula, right? Now 5, maybe because you got confused with the algebra. You got confused with the x power 5 that we use. Okay, because we have to get 6 equations, so probably you got confused with that. And I agree, maybe you had an issue with that. Majority of you answered 6, so let's just stop sharing the result. Okay, we have to compute for your 3-point rule. Your f of x's are going to be 1, x squared, x power 3, and x power 5. Probably you saw this 5 here and you decided to pick 5. Okay, but what is your rule like? Okay, so integral of f of x minus 1 to 1 dx is going to be equal to lambda 0 x 0, lambda 1 x 1, lambda 2. Okay, so there is an f which I keep forgetting, f of x1, f of x3. Probably I should write it neater, maybe. Okay, so here we have a lambda 1 f of x1 plus lambda 2 Okay, you start with the lambda 0, right? Lambda 0, lambda 1, f of x1 plus lambda 2, f of x2. Okay, so that's what you're going to get. What are the parameters? Lambda 0, lambda 1, lambda 2, x0, x1, x2. So you're 1, 2, 3, 4, 5, 6, 6 parameters, and that's the answer. Okay. Okay, so let us do the next last poll, I think. Yeah, last poll that we have. So how many unknowns would we have in the 1-point rule? Okay, how many unknowns would we have in the 1-point rule? Is it 1, 10, 2, 0, or 3? At least try to answer this properly, okay? Because we've done some tough questions previously. So let's try to get, okay, let me just start off this poll. Yeah. How many unknowns would we have in the 1-point rule? 1, 10, 2, 0, or 3? Forty seconds left. Fifteen seconds left. Okay, I'll give you 10 more seconds and I'll end the poll. Okay, I'm going to stop the poll now. And I will show you the results. Majority of you guys answered 2. But like seriously, why are you guys answering 1, 0, like 0? 0 unknowns? How does that even make sense? Like, how does it make sense to answer 0? I feel like you're just doing this so that, you know, you could just get over with it. Okay, how many unknowns would we have in the 1-point rule? Okay, we have 2 unknowns in the 1-point rule. Let me just write it for you. Okay, so integral from -1 to 1 f of x dx is equal to what? Lambda 0 f of x0. So what are the unknowns that we have? We have lambda 0 and we have x0. Okay, so those are the 2 unknowns that we have. 2 is the correct answer. Okay, so with this, it is a wrap for today. Okay.